A continuously variable transaxle, CVT for short, will soon be introduced on Chrysler Group vehicles. There's a basic difference between the way CVTs provide a range of ratios and the way conventional electronically controlled automatics do. On conventional automatics, clutches drive or hold parts of planetary gear sets, which provide distinct gear ratios. On CVTs, a continuous range of ratios is provided by two pulleys and a special steel belt. The primary or input pulley pushes the belt, which then turns a secondary or output pulley. As the sides of one pulley get farther apart, the sides of the other one get closer, changing the working pulley diameters and providing a change in ratio. Welcome to Mastertech. This month we're going to take a preliminary look at the continuously variable transaxle. We'll begin with an overview of the CVT that includes what drivers might experience in a vehicle equipped with one of these transaxles. Then we'll cover CVT components and operation. We'll wrap things up with a look at maintenance, diagnosis, and service. Let's start off our overview of the CVT with identification. It's easy to see that a vehicle is equipped with a CVT. The shape of the case is unique, and you're not likely to mistake it for anything else. There's also the standard Chrysler identification label located on top of the transaxle with a serial number and other information. The first Chrysler Group vehicle to use the CVT will be the 2007 Dodge Caliber. At the Caliber launch, the CVT will be offered behind 2-liter and 2.4-liter engines. The main advantages of the continuously variable transaxle are efficiency and smooth operation. First of all, CVT's wide range of ratios contributes to fuel economy. CVT ratios range from about 2.3 to 1 for low to an overdrive ratio of about 0.4 to 1 in high. The CVT is designed so that acceleration demands are met using continuously variable ratios along with engine speed that ramps up quickly instead of discrete gears and a series of increases and decreases in engine speed. Meeting acceleration demands in this way has several advantages. Because the engine operates in an efficient RPM range longer, one result is better fuel economy. Because of continuously variable ratios, another result is a smoother transition from low ratio to high. Both the efficient use of engine RPM and continuous ratios also contribute to smoother operation when the vehicle is climbing hills or towing a trailer. An additional advantage is excellent performance. Because of the way a CVT operates, the torque converter clutch can engage earlier during acceleration and disengage later during braking. This also contributes to fuel economy because early engagement minimizes slippage in the torque converter, and later disengagement allows the PCM to prolong D-cell fuel shutoff. As you might expect, CVT operation is going to feel a little different to drivers, and customers may have questions based on those differences. Because the transmission ratio and engine speed change smoothly to respond to power demands, under most circumstances, drivers will not notice distinct shifts. So service advisors or anyone else who deals directly with customers should be prepared to explain the typical driving experience. One exception to the stepless transition occurs if a driver depresses the pedal to the wide open throttle position. Toward the end of accelerator pedal travel, the linkage engages a spring-loaded plunger to alert the driver of imminent wide open throttle and a kick-down type change in transaxle ratio and engine speed. Another exception is auto stick mode, which provides 6 distinct ratios. We'll discuss auto stick in greater detail later. That's an overview of the advantages of the CVT and what drivers might experience. Next, we're going to take a closer look at CVT components and operation. In some cases, CVT components are like those used on other transaxles. And in other cases, they're very different. For instance, the torque converter and converter clutch are similar to those in other automatic transaxles. On the other hand, the pump is off-center and driven by a chain instead of being driven directly by the torque converter hub. It also maintains higher system pressure than conventional pumps. Regulated line pressure can be up to 750 psi. One critical difference between the CVT and conventional automatics is the fluid. CVT automatic transmission fluid is unlike any other ATF, and its green color is used to help identify it. CVT F+4 has unique friction characteristics, and the use of any other fluid will damage the transaxle. Although the green color is useful in identification, remember, as with all automatic transmission fluids, CVT F+4 will darken with age. Two filters are used to help keep the fluid free of contaminants. A screen is used in the oil pan on the pump pickup, and there's a non-serviceable paper filter behind the onboard cooler. As its name suggests, the onboard cooler is located on the transaxle. Engine coolant that circulates around fluid passages helps warm the fluid in cold weather. A pressure-operated bypass valve prevents fluid from reaching the air-to-oil cooler when the fluid is thicker due to cold ambient temperatures. The air-to-oil cooler is part of the vehicle cooling module. The continuously variable transaxle uses clutches to transfer power from the torque converter to the pulleys and belt. Forward and reverse clutches are coupled to a planetary gear set, with the planetary annulus acting as the input from the torque converter. The reverse clutch holds the planetary carrier, which reverses the direction of the sun gear and of the primary pulley. In reverse, the ratio of the planetary gear set is 0.745 to 1. The forward clutch locks the planetary gear set together for a 1-to-1 input ratio. The transaxle is in neutral when neither clutch is engaged. At the heart of the CVT is the pulley and belt system, referred to as the variator. The primary or input pulley has a fixed side and a moving side, which is positioned by hydraulic pressure. The belt consists of approximately 400 segments held together by two sets of 12 steel bands. The bands fit into grooves in the segments. The segment sides have serrations, which, like the tread on a tire, allow them to grip the pulleys. Like the primary pulley, the secondary pulley has fixed and moving sides. However, the locations are switched. When the vehicle accelerates from a stop, the primary pulley sides are farther apart, which in effect means that the belt is being driven by a smaller diameter pulley. The secondary pulley sides are closer together, so that the belt is driving a larger diameter pulley. This provides a low ratio. As vehicle speed increases, the primary pulley sides move closer together, while the secondary pulley sides move farther apart. This change in effective pulley diameter allows the variator to progress through 1-to-1 and then overdrive ratios. Once past the secondary pulley, power flow is similar to that of a conventional automatic. The shaft that supports the secondary pulley has a final drive output gear and supports the park gear. The final drive in the CVT is similar to that found in the conventional automatic. Note that due to an extremely low overdrive ratio, the CVT final drive uses a high numerical ratio, around 6-to-1. The shift lever and manual valve, plus the Global Powertrain Engine Controller 1 and the CVT control module all play a part in controlling the flow of power through the CVT. Primary control of the input clutches is through the shift lever and manual valve. However, under certain conditions, the controllers can prevent clutch engagement, such as when a shift into reverse on a vehicle traveling forward would damage the transaxle. As mentioned earlier, hydraulic pressure positions the moving sides of the pulleys. This clamps the belt against the fixed sides and establishes the working diameters. Hydraulic positioning of the primary pulley determines the ratio, and the higher pressure used on the primary side to position the belt forces a change in the position of the secondary pulley. The hydraulic clamping of the secondary pulley is proportional to engine torque. The Global Powertrain Engine Controller 1, or GPEC 1, and the CVT control module work together to control pulley position. The CVT control module, located under the instrument panel on the driver's side, provides direct control, regulating and routing fluid pressure by means of 4 solenoids and 2 pressure sensors located in the valve body. The fluid control is in response to messages that the CVT control module receives over the CAN-C bus from the GPEC-1. The GPEC-1 bases the progression of the ratios from low to high on models of vehicle operating conditions, called variograms. These variograms map out the required change in ratio and engine speed according to torque demand. With a large torque demand, the ratio progression allows engine speed to climb quickly. With a small demand, ratios result in engine speed climbing more slowly. The variograms map out a number of torque demand scenarios with ratio progressions to match. Besides torque demand, the ratio progression in the CVT is also affected by the mode of operation selected by the driver. The drive position is used for most driving, and the ramp up in ratio and engine speed is designed to provide fuel economy. On calibers without auto stick, there is also a low sport position indicated by an L sub S. Low sport uses a more aggressive ratio selection to provide quicker acceleration and more engine braking. Keep in mind that one big difference between CVT low sport and low on conventional automatics is that CVT low sport does not limit the transaxle to only lower ratios. The complete range of ratios is still available. On some calibers, the CVT is available with auto stick. In that case, there are plus and minus selections on the sides of the drive position that correspond to upshifts and downshifts. Once a driver initiates auto stick by pushing the shift lever to the side, it offers manual selection of 6 distinct ratios. Except in special cases, when the transaxle is in auto stick, the ratio changes only with driver input. To inform the driver of which ratio the CVT auto stick mode is in, the CVT control module sends a message over the CAN-C bus to the Totally Integrated Power Module, or TIPM, which is the gateway module on caliper. The TIPM, in turn, sends the information over the CAN-B bus to the cabin compartment node, or CCN. The cluster, which is part of the CCN, displays the selection. That, briefly, is how the CVT operates. Next, we'll take a look at CVT maintenance, diagnosis, and service. There really isn't a lot to remember regarding scheduled maintenance and the CVT. Under Schedule A, the transaxle is fill for life and requires no scheduled maintenance. Schedule B, severe service, requires changing the fluid and pan filter every 60,000 miles. As with other vehicles, there are towing precautions you need to be aware of. For one thing, do not flat tow any vehicle equipped with a CVT. When it comes to diagnosis, you're going to notice some differences between the CVT and conventional electronically controlled automatics. First of all, the CVT does have limp-in operation, but it varies with the type of condition and its severity. At one extreme, if a severe condition is keeping the powertrain from operating as it should, the GPEC-1 will limit engine power to the transaxle as well as limiting ratios. This will prevent the vehicle from maintaining higher speeds. On the other hand, with a minor condition, there may not be much difference between limp-in and normal operation. In fact, in some cases, the only evidence of a condition requiring diagnosis may be mill illumination when the GPEC-1 or CVT control module records a diagnostic trouble code. You can use the service information as a guide to both limp-in symptoms and to procedures for investigating codes. And as with other CAN bus systems, you can retrieve DTCs with the STAR scan or with the STAR mobile. Part of diagnosis may involve checking the fluid level. However, because the transaxle does not normally require that the fluid be checked and topped off, there is a cap on the filler tube instead of a dipstick. As with LX models, the dipstick is an essential special tool that is used only during service. Note that the tool is a universal design, not intended to be inserted fully into the filler tube. If you do need to add fluid to the transaxle, once again, use only CVT F+4. Use of any other fluid will damage the transaxle. In addition to establishing that the transaxle has the correct amount of fluid, some diagnosis may involve making sure that it is supplying fluid at the proper pressure and at the right time. To aid diagnosis, the CVT is equipped with 7 pressure test ports. If you do need to check pressures, however, keep in mind that you'll need new special tools to handle the higher pressures. These include the gauge assembly and pressure test adapters. Refer to the service information for additional details. When it comes to servicing the CVT, be aware that, as with many new assemblies, the warranty policy for the CVT is special. So be sure to refer to the warranty bulletin for service guidelines. If service does involve replacing either the Transaxle or CVT control module, the control module will need to relearn the calibration value stored in the Transaxle. Use the star scan and the service procedures on TechConnect to do this. And for training on additional aspects of the continuously variable Transaxle, be sure to keep an eye out for a Daimler Chrysler Academy New Technology course, which has the CVT in its description. That's it for this month. Be sure to check back next month when we'll be going into the GPEC 1 in greater depth, along with a new family of 4-cylinder engines.